Hi, thanks for joining me. This is Cheng, a PhD from Iowa State University. Today, I'm going to present LogExtractor. This is a joint work with Chen and my advisors, Professor Zhenqiang Gong and Professor Yong Guan. The project is cooperative with NIST researchers, Barbara Goodman and James Lyle, and sponsored by NIST Syste, Center for Statistics and Applications in Forensic Evidence. We propose LogExtractor as an automated approach for identifying and extracting digital evidence from Android log text corpus. Searching evidence in the text corpus is one of the most popular ways when forensic practitioners look into the mobile devices. According to Android, an Android app data flow analysis study in 2016, by analyzing around 23,000 real-world apps, it finds logging system is the primary place where apps save evidentiary data such as GPS location and network information. That is to say, when a forensic analyst investigates the mobile device, log message has the highest chance to contain the useful digital evidence. Here, let's work through the scenario of evidence identification from logs. First, the forensic investigator dumps the log from the suspect device by using tools such as Android Debug Bridge. Next, with the extracted log messages, the investigator can adapt software to search by keyword or regular expression to locate and retrieve the evidence. Following the aforementioned introduced scenario, let's take a look at this piece of real-world log message. If you were a forensic analyst working on this, how and how fast would you find the evidence from the log message? Well, probably you can come up with techniques such as keyword searching or regular expression mappings. But let's look at this closely again. Given that you find these are GPS coordinates, by which patterns would you use to parse this information? And imagine if there is no keywords like location show up, it will be more difficult to catch this part when dealing with the real-world size log corpus, which is often more than 10,000 messages. Let me use this example to rephrase and motivate our research problems. Given that a forensic investigator wants to find the evidence from log message A and B, our first research problem, evidence identification problem, is to find which message contains the evidence. And if the answer is yes, what types of evidence they are. In this case, given that we find out message A contains the GPS latitude, what's the actual value is supposed to be? Here, the evidence extraction problem comes, which targets at answering this kind of question. Using the aforementioned example for message A, let's quickly go through the example to see how an ideal automation tool like LogExtractor should work for extracting the actual evidence on the log message body part, which is highlighted in orange. Later, we will repeat this example with more technical details. Given LogExtractor has the analysis result as the state diagram in the center, an input string at the bottom left. We work the state diagram based on the input character one by one, then output the result at the bottom right. So here we place an automation to see the result. So as you can see, with such a state diagram, we can successfully extract the latitude value, which is 30.03 from the input string. Our research purpose is to use LogExtractor to answer both evidence identification an extraction problem. We find that existing studies are limited at solving their specific domain problems, but cannot help us to solve evidence identification and extraction problem in Android logging system. For example, the Android app Taint analysis studies, such as FlowJoy Android Safe, as the right-hand side figure demonstrated, can only tell which type of data can be found at which category of sink, like the file system. Unfortunately, they do not support the output as detailed as the log message string patterns. On the other hand, string analysis studies like JSA and Violist do support string pattern analysis, but do not answer which piece inside the string patterns carries which type of evidence. Log parsers, unlike aforementioned approaches, implement the analysis based on the data mining, which builds their analysis logic on historical data. However, while it does use techniques like regular expression to catch frequent use evidence, it still lacks the ability to answer evidence extraction problem without keyword hints or manual operations. Therefore, we propose LogExtractor for solving our research problems. Before diving deep into the research details about how we build the automatic extraction tool, I would like to give a quick review on Android log message. As the example shown, a log message is composed by timestamp, the process ID, the text ID, log level, log tag, and body message. While timestamp, process ID, and the task ID are determined by runtime, an Android app can decide the log level, tag, and body by selecting the corresponding API and variables. And here is our proposed scenario with the help from LogExtractor. After the forensic investigator obtains the log message from the suspect device, LogExtractor automatically identifies the evidentiary log messages and extract the evidence like GPS location as shown in the example. So now the problem is how to generate this kind of patterns. So next we will present how we generate the patterns here for matching and extracting the evidence. We propose to build app log evidence database in the offline phase by analyzing real-world apps. Each entry in the database represents a log message pattern, including log level, the string patterns of log tag, and log body that may be written into logging system during the runtime. The log string pattern is summarized as Tainted DFA, which will be covered later. The workflow at the bottom demonstrates how we use this database to identify and match the evidence from log messages. To build the app log evidence database, as part of the LogExtractor, we propose to apply a composition of string and Taint analysis over Android app program code. That is, we analyze Android APK files collected from real-world market, such as Google Play Store. Then, for each logging system API that writes the log message, we output the log message patterns. So here, let's use a program code example to demonstrate this. So first, we initialize, so as you can see in the line 2, we initialize a string constant without Taint first. So here we have a variable tracking the string variable LAT and hyphen. Then we propagate it into the string buffer. So here is another variable with floating number string pattern and carrying the latitude type. Let's use latitude with angle brackets to represent it. Then we combine them together and propagate the result to the output buffer. So that's the overview. And now before moving to the tainted DFA, let's first look at the DFA. So a DFA, a deterministic finite-state automaton, is functionally equivalent to the regular expressions, like these two examples. When we match an input string with the DFA by working from a state to another state, one character is consumed from the input string. At the end, if one can reach the end state denoted by the double circle, such as S4 state, and the input string become empty, then we can conclude they are matched. This is the tainted DFA representing our previous example. So as you can see, the left-hand side is the part for the constant string, LAT and hyphen. And the right-hand side is the floating number string with evidence type latitude. So beside the DFA, we add a Taint table for each state within the DFA to track evidence type propagation in the app program. In this example, any character being matched by the right-hand side will be a part of the latitude string output. So by using that tainted DFA, we summarize there are three scenarios when using the tainted DFA to extract the evidence string from the input. So note that the evidence type isn't necessary to be single type like the latitude that we previously demonstrated. This work can also support the case when the input string carries multiple evidence types, like the text input or the unique identifier. So when extracting the string, we keep tracking two pointers. One points to the current state after consuming an input character, while the other one points to the previous state. In this scenario, since we just moved from a state without evidence to the one has certain evidence type, we initialize the output buffer. And following the previous one, if both pointers point to states with the same evidence type, we shall append the input character to the output. This scenario suggests that. So as you can see, so here the first one is the tainted one, and the next one is the one without the taint, which means the first one has the evidence type state, but then the following one doesn't. So in this case, suggests that the input character T3 should not be counted as the evidence string, and we should stop the buffering and output the result. So let's wrap up the scenarios introduced earlier and work through this example again. So this is the example that we, by analyzing the program code, and we get this tainted DFA. So if you remember it, the left-hand side is the constant string, and the right-hand side is the floating string with the evidence type latitude. And suppose we have an input string like the button shown. So here, we start from the initial pointer. So next, since the from the S26 to S27, there is a uppercase L, so that we consume character L and move to the next state. And since these two states are the states without the evidence type, then this character should not be counted as any kind of evidence here. And next is the A and T and hyphen. So when we move to the hyphen, then okay, this is the first scenario that we earlier proposed. So we move from a state without the evidence type to a state with the latitude evidence type. So after consuming the hyphen character, we're supposed to initialize an output buffer And you can see it at the bottom right, like this. Then we consume the number 3. And since this is the scenario that 2 states have the same evidence type latitude, so number 3 should be counted as part of the latitude value here. So we keep appending the output from the input string. So until we reach the end state of this tainted DFA, and since you can see the input string here is empty, so which means we finish extraction and we can output this value as a result. So we evaluate a LogExtractor on both benchmark apps and real-world apps. For benchmark apps, we use Troy Bench. And we count only the apps that are writing logging message only. And at the end, we found there are 65 apps. As you can see, the identification and extraction performance are quite well. There are some technical limitations deteriorates the performance, like ICC flow. It's a intercomponent communication between the different Android components. And we inherited this limitation by the tool we use, FlowJoy, to construct the code graph. And also, there are other limitations like the implicit flows that are well-known challenges in Taint analysis. And also, since we lack the precise string models of Java string libraries like the formatter and matcher, some patterns are wrongly constructed. And the real-world app evaluation is conducted over 12,000 apps. We manually verify 91 apps and got similar performance report like the benchmark apps. There are 2 additional limitations found in the real-world apps verification. One is the string model precision on 2-dimensional data structures such as map. And the other one is the any string DFA, which by any string, it means it's a regular expression. You can imagine this as a regular expression that can accept all the string. So in this case, if there are the API method that we fail to assign a proper string model, then it will deteriorate the performance, because then we keep the system consistent and treating as any string model. And you can imagine that by this case, we will merge all evidence type together and output the result. So in this case, it will cause the false reports. And before concluding this study, I wish to use some real-world log message that were found in our manual verification to highlight LogExtractor contribution to our research problems. These are the real-world log message that carrying GPS location data. As you may find, the first one looks straightforward and can be easily found given the searching keywords are correctly used. Next, we find a case where GPS coordinates appears without the keyword. However, due to the separator and their appearing sequence that latitude goes first, then longitude, we believe this may cause for the investigator extra effort to find, but it is not impossible to find. So the most interesting one comes here, the next one. We also find a case where there's no keyword, like location, like GPS, like latitude, there's nothing there, but just a comma. And these are just comma separated string. And coordinates order do not appear as the other generally used patterns, like you always goes with latitude and the longitude. So in this case, the LogExtractor reports that actually the first one is the longitude, then it goes with latitude. So we believe it is very challenging for human investigator as well as other existing forensic analysis tools to determine the correct GPS coordinates from the log message. So, and here, this is how we introduce LogExtractor to play an important role when being used to automatically extract the evidence from the text string. So to sum up, our proposed framework, LogExtractor, combines string and Taint analysis to build the app log evidence database. With that database, we present how to match and extract the digital evidence from the log message dumped from the suspect device. At the evaluation part, we demonstrate how LogExtractor can help with retrieving the real-world GPS location evidence, which human and existing software tools are limited to catch. In the future, we aim to keep improving the time and space efficiency when applying LogExtractor on analyzing real-world apps. Also, we will work on extending our existing string analysis model by the one with higher precision. So thank you for joining this presentation again.